When we think of very windy places, we usually imagine somewhere like the Sahara Desert or the flatlands of Kansas, where high-pressure air from the interior of the massive landmass is free to blow outwards. But nowhere on Earth has winds that could compare to the speed of the fastest winds in the solar system, which are found on a sideways planet called Uranus. This is a place so frozen and distant that not even sunlight can warm it up. Yet somehow it has sustained speeds of 900 kilometers per hour. Why? Winds are generated by differences in atmospheric pressure. Areas of high pressure want to move towards areas of low pressure, and they do so by pushing against each other. The air molecules themselves don't actually travel very far. They just collide with ones next to them, and those collide with ones next to them, creating a domino effect that pushes air masses across the planet. So when an area of high pressure turns into an area of low pressure, all the air molecules around it get pushed outward at once, creating a strong wind. Here on Earth, there are lots of things that can cause these temporary but sometimes quite intense variations in air pressure. But for the most part, our planet's air pressure is pretty evenly distributed because it's warmed by the nuclear fusion reactions happening at our core. That energy makes its way up to the surface, keeping the molecules in our atmosphere bouncing around with enough energy to maintain a relatively constant state of moderate pressure everywhere. This is called a convection current. Hot stuff rises and cooler stuff sinks, and that creates an endless cycle of rising and sinking that spreads heat and therefore higher air pressure around the planet. But Uranus isn't like Earth. It's an ice giant. Its insides are mostly made of water, methane, and ammonia in their solid, icy forms, which means that there isn't any heat to spread. There is some leftover heat from when it formed, but that's not nearly enough to maintain any kind of convection current. Instead, Uranus has convection currents of cold, which means that the icy mantle slowly sinks toward its core while new, colder ice forms on top of the old. And if there's no heat to warm the air and drive convection currents, then what's driving the winds on Uranus? Well, back in the 1970s, scientists realized that the swings in Uranus' atmosphere from extreme cold to extreme heat must have something to do with the planet's magnetic field. Uranus's magnetic field is perfectly offset from its rotational axis, meaning that the planet's rotation itself cannot be responsible for generating it. Instead, it's probably generated deep inside the planet by the movement of its metallic hydrogen core. Because this magnetic field is misaligned, it causes charged particles from the Sun to hit Uranus off-axis. And because Uranus rotates so quickly, those particles get flung away from the planet almost as fast as they arrive, building up an electric potential on the planet's surface. Eventually, the electric repulsion between the negatively charged particles on the surface and the positively charged particles in the upper atmosphere becomes strong enough to generate winds. This is called the dynamo effect. The problem is the dynamo effect doesn't explain why the winds remain so strong. After all, electric potential only does work when there's a difference in potential. So why doesn't the electric potential generated by Uranus's dynamo effect just even out over time? Well, we might have an answer for that. According to researchers from the University of Berlin, mountains on Uranus could be disrupting the flow of charged particles and preventing them from mixing together. Just like how mountains on Earth disrupt wind patterns by forcing air masses to rise and fall over them, mountains on Uranus could be disrupting the flow of charged particles and creating pockets of different potentials. Where the particles collide, there will be an exchange of energy that generates new kinetic energy for more wind. Scientists think these mountains may be the remnants of ancient impacts that never really got smoothed out due to the lack of heat in Uranus' atmosphere. And computer models have shown that these mountains could be big enough to disrupt the flow of particles and maintain strong winds. But wait, let's go back to the start here. Why are the winds on Uranus so fast in the first place? Well, part of it comes down to something called the Coriolis effect. On Earth, the Coriolis effect happens when air masses are deflected to the right of their path of motion in the northern hemisphere and to the left of their path of motion in the southern hemisphere. It's because as Earth rotates, different latitudes move at different speeds. The further you get from the equator, the slower the rotational speed. So air masses moving north or south will change in speed as they encounter different latitudes, causing them to curve. On Uranus, which rotates faster than Earth, the Coriolis effect is stronger. So when air masses collide with each other, they deflect off one another more strongly, resulting in more intense winds. Plus, the flatness of Uranus means that there aren't any mountains or valleys to disrupt the flow of air. On Earth, air masses often slow down when they encounter mountains because they reforce to rise up and over them. But without mountains, the air masses on Uranus keep colliding with the same particles over and over again, keeping their momentum high. There's also something about Uranus's magnetic field that funnels charged particles towards its poles. This focus of charged particles could also be contributing to the formation of mountains at the poles, which could be forming through volcanic activity driven by the heat generated from the impact of charged particles. These mountains could also be disrupting the flow of charged particles and leading to the maintenance of high-speed winds at the poles. Basically, the combination of these factors means that once a wind starts blowing on Uranus, it tends to keep going for a very long time. In fact, it could be going for billions of years. All this talk of windy planets got us thinking about windy places here on Earth. Did you know that the strongest wind ever recorded was on the surface of Jupiter's moon Europa? If you want to learn about that and other amazing discoveries from the space in the last year, check out our end-of-year special. You'll hear about the James Webb Space Telescope's first images, the discovery of water on the moon, and the year in spaceflight, including every rocket launch of 2022, and if you have your own questions about space, you can send them in and our experts will do their best to answer them. Thanks for watching.